For as long as we've been around, one of nature's deadliest forces has hit us without any warning at all. But today, we're diving into a revolutionary and, yeah, some would say controversial, new science that's aiming to finally crack the earthquake code.
I mean, really think about that for a second. We can track a hurricane for days, watching its every move, giving everyone time to prepare. But an earthquake, which can be just as deadly, if not more so, it just happens. No warning. So why the huge gap? It's a question that has honestly baffled scientists for a very, very long time.
And this really gets to the heart of the problem. You see, traditional seismology is all about probabilities. It's kind of like an insurance company. It can tell you statistically how many people are likely to have an accident this year, but it has no idea who it will be. Seismologists can tell us the long-term odds for a region, but they can't tell us, hey, this specific fault is about to go. And to save lives, we have to move from guessing games to actual prediction.
So here's how we're going to break this all down. First, we'll talk more about that prediction gap. Then we'll get into the core theory, this idea of the rock battery. After that, we'll look at the cascade of signals it supposedly produces, how that might lead to a real forecasting system, and finally, what it really means to challenge the scientific status quo.
All right, let's dive right into section 1, the prediction gap. The big problem with how we do things now is that we're basically waiting for the rock to start breaking. We're listening for the rupture itself to kick off. By then, of course, it's way too late.
And when that rupture finally happens, the stakes are just immense. A magnitude 9 quake unleashes the energy of 2 million atomic bombs. Think about that. All that power building up underground, and we get zero warning that it's about to be released. It just tells you we've probably been looking in the wrong place, or maybe for the wrong thing. We need clues before the first crack appears.
And that brings us to the core idea here, the big breakthrough. Section 2, the rock battery. This is a completely different way of thinking about what's happening to rocks when they're under incredible tectonic stress. This quote from physicist Friedemann Freund, the guy who came up with the theory, says it all. What he found was that when you put rocks under that kind of incredible pressure before a quake, they don't just sit there waiting to snap. No, they fundamentally change. They start acting like a giant semiconductor battery.
Okay, so how does this actually work? It boils down to a 4-step process. You start with normal, stable rock. Then, tectonic forces start putting on the squeeze. This pressure wakes up these dormant little defects in the mineral crystals called peroxy bonds. And when those bonds break, they release electrical charges. Now, this is where things get really, really wild. One of those charges, the electron, gets stuck. But the other one, something called a positive hole, is free to move. And man, does it move. We're talking 200 meters per second. These charges can flow right out of the stressed rock, deep in the earth, and travel for over 100 kilometers. The rock itself becomes a giant underground power source.
So, okay, if this massive battery is charging up miles below us, can we actually see anything? Does it give off any signs we can pick up on the surface? Well, the answer seems to be a resounding yes. Let's look at the cascade of signals.
Well, the first signal is something we can literally see from space. It turns out that before a big earthquake, satellites have spotted something really weird. The ground itself starts to glow in infrared light.
And the key thing to understand here is this is not heat, it's a quantum thing. When those positive holes come streaming out of the deep rock and hit the surface, they release their energy as infrared photons, as light. It creates a very specific light signature that's totally different from just, the ground warming up.
And this isn't just a theory in a lab. We have a tragic, real-world example. In the days before the terrible 2009 L'Aquila earthquake in Italy, satellite data picked up this exact infrared signature. The mountaintops, where these charges tend to gather, were literally glowing, described as shining, as if they were set ablaze. All right, the next signal is, well, it's even more mind-bending, honestly. The effects of this underground battery don't just stop at the surface. They can actually reach all the way up to the edge of space, into the ionosphere.
So here's the crazy chain reaction that happens. These positive charges build up on the ground and create a huge electric field. This field is strong enough to rip electrons off of air molecules. You get this giant bubble of positively charged air, and because like charges repel, this bubble starts rising up through the atmosphere. When it gets high enough, it actually messes with the plasma in the ionosphere, creating a disturbance we can measure.
And again, this isn't just something on a whiteboard. It's been seen in the wild. Before a massive magnitude 7.9 quake in Alaska back in 2002, GPS satellites detected a huge anomaly in the ionosphere's electron content, and it was sitting right over the spot where the earthquake was about to happen.
You know, what's so powerful about this one idea is that it could be the master key that unlocks a whole bunch of other mysteries. Those strange earthquake lights people have reported for centuries? Yeah, that could be it. The widespread reports of animals freaking out before a quake? They might be sensitive to these electric fields. Even spikes in human health issues. It could all trace back to these powerful electrical forces coming from deep inside the Earth.
Okay, so that's the science. But here's the billion-dollar question, right? Can we actually use all this to build a real-world warning system? This is where we talk about forecasting the future. So the strategy here, which is now getting backing from folks like NASA and the European Space Agency, isn't about finding one single magic bullet signal. It's a multi-pronged attack. If it's too cloudy to see the infrared glow, you look at what the ionosphere is doing. If a solar storm is messing with the ionosphere, you check other signals. The whole idea is to build a strong case from several different independent lines of evidence. And we need to be really clear about the goal here. It isn't about predicting the exact second a quake will hit. The goal is to be able to issue a high-confidence warning, say 2 to 7 days out, that the probability of a major earthquake in a specific area has just gone way, way up. That kind of heads up, that's enough time to prepare. That can save an incredible number of lives.
So, finally, let's just step back and think about what it means to challenge the system with an idea this radical. Because this isn't just about earthquakes anymore. This could be a whole new chapter in how we understand solid-state physics.
You have to remember, for decades, this stuff was way out on the fringe. It was dismissed by the mainstream. But as one of the earliest supporters, retired USGS geologist John Deere, said, "The Earth is stranger than we give it credit for." And that's a perfect reminder that science only moves forward when people are brave enough to challenge what we think we already know.
So what this new science is really telling us is that before the Earth breaks, it whispers. It sends out this cascade of electrical warnings. The signals have probably been there the whole time, just written off as weird stories or data glitches. And that leaves us with one last big thought. If rocks can talk, are we finally, after all this time, learning how to listen?